Implicit differentiation problems can be kind of a tough topic in calculus, and once you get that down, some problems even take it a step further and make you use the information you've figured out from that implicit differentiation problem to create the equation of a tangent line to a function, which pretty much just adds in a little bit more confusion and extra steps at times, which pretty much just adds in some extra steps and at times even a little bit of confusion. So I wanted to break it down for you, show you the exact process that you can easily follow to find the equation of a tangent line to a curve at a given point using implicit differentiation. And this was actually one of the problems that I did in one of my recent live streams that I'm doing every Monday night at 5 Pacific, 8 Eastern. So let's go ahead and jump into the problem, and hopefully you'll join us next week for the live stream. So the problem we're going to be doing here is use implicit differentiation to find an equation of the tangent line to the curve at the given point. The equation that we are given is y times sine of 2x equals x times cosine of 2y. And the point that we are given to find the tangent line at that point is pi over 2, pi over 4. So the x coordinate of pi over 2, y coordinate of pi over 4. Really, with these types of problems where you're asked to find the equation of a tangent line to the curve at a given point, it's going to take the exact same process as the first problem we did here, and it's just going to build on that a bit. So what you want to think about basically is we're going to start obviously with just implicit differentiation. So if you're not really told which letter is your function and which letter is your variable, you know, sometimes it may say find dy dx. In this case, they didn't do that. They just gave us some equation with x's and y's. Typically, you can assume that x is going to be the variable and y is going to be the function. And the reason for that, and of course, that's assuming that you are given some equation that has x's and y's. The reason for that is typically a function with x's and y's is going to be graphed on an xy axis, where x is always the independent variable, the input variable, and then y is always the dependent variable or the output variable. So as a result, we always want to take the derivative of both sides with respect to our variable, which, since we're going to be able to assume that x is our variable, we'll take the derivative with respect to x. So again, this is another example where we're going to have to apply product rule. And in fact, we are actually going to have to apply product rule and chain rule on this one. So this is going to be kind of an interesting example. So you can see on both sides of our equation here, we have a product of two separate functions. So we're actually going to have to do product rule twice, once on each side of our equation here. So we'll start with our left side. We're going to, again, break it down into f and g. So f we'll just say is y. G we'll say is sine of 2x. F prime is going to be the derivative of f, which, again, since we have our function, we have our function we're taking the derivative of with respect to our variable. Since we don't know what our function is, the best we can do is to say the derivative of y with respect to x. Then we're going to find g prime, which is just the derivative of sine of 2x. And to find the derivative of sine of 2x, we're going to have to use chain rule. So the chain rule says take the derivative of the outside function, which is going to be the sine. Since we have this 2x within the parentheses here, it's usually going to be what's in the parentheses like that. That's going to be your inside function. So our outside function is the sine piece. We're going to take the derivative of sine. So the derivative of sine is cosine. And then we're going to leave the inside function alone. So leave 2x as 2x. And then multiply that by the derivative of the inside function. Well, the derivative of 2x is just 2. And then by product rule, we have to cross multiply these and then add them together. So y times cosine 2x times 2. So that'll just give us 2y cosine of 2x. And then plus sine of 2x times dy dx. And that'll be the derivative of the left side of our equation. So now on the right side of our equation, we are again going to have product rule. So we'll go ahead and just call f the x function here. And we'll call g the cosine of 2y. Then we need to find our f prime and our g prime. So the derivative of x is just going to be 1. And then the derivative of cosine of 2y is going to be a little bit more complicated, because unlike over here where we had just our variable, just x's, taking the derivative with respect to x, over here we have y's, we have our function. So the derivative of cosine 2y is going to be a little bit more similar to taking the derivative over here. So again, we're going to have chain rule because we have this 2y being plugged into the cosine function. So first of all, we're going to take the derivative of our outside function, which is cosine. The derivative of cosine is negative sine. We're going to leave our inside function the same by chain rule. And then we're going to multiply that by the derivative of our inside function. Well, the derivative of 2y with respect to x is just going to be 2 dy dx. Since we don't know y, again, we can't know its derivative, but we can say the derivative of y with respect to x. So then by product rule, we will cross multiply these. So we will get x times all this stuff. So we're going to have negative 2x. So the negative 2x times sine of 2y times dy dx. And then we're going to have 1 times cosine of 2y, which is just cosine of 2y. So then we're going to add in cosine of 2y, and that is due to the product rule. So now we've taken the derivative of both sides of our equation. So now what we can do, just like we did before, is we're going to move all of our dy dx terms to one side of our equation. We'll go ahead and move it over to the left, and all of our non-dy dx terms over to the right. So we'll put our dy dx's to the left. This term is going to have to move over to the right. So we're going to minus 2y cosine of 2x from both sides, minus 2y cosine of 2x from both sides. And then we need to move this over to the left. So we're going to add 2x sine of 2y dy dx to both sides. So plus 2x sine of 2y dy dx. And what that is going to do is it's going to cancel this over on the right side of our equation. It's going to cancel this over on the left side of our equation. And we are just going to have 2x sine of 2y dy dx plus sine of 2x dy dx. And then we will set that equal to what we have over on the right now. At this point left is the cosine of 2y minus 2y cosine of 2x. All right. And then once we have all our dy dx terms over on the left side of our equation, again, what we can do is factor out our dy dx, because now both of these terms have a dy dx in common. And that's going to accomplish exactly what it did in the first problem we did here today. And that is going to be making so that we only have a single dy dx term left that we can then solve for much more easily. So if we take dy dx out of this first term, we're going to be left with 2x times sine of 2y plus sine of 2x. And then on the right, we're still going to have nothing different. And then we can divide both sides of our equation by everything within the parentheses here, because dy dx times all this stuff, we can divide it over to get the dy dx all by itself. So our numerator is just going to be whatever we had on the right before. And then plus 2x sine of 2y plus sine of 2x. So there's our dy dx. But remember, there is a little bit more to this problem, because what they told us to find was the equation of the tangent line to the curve at the given point. So now we have dy dx. Well, what you want to think about is, what is a tangent line? Well, a tangent line is just a line that shares two things in specific with the curve that you're making the line tangent to. So those two things are going to be that it has to share a point, it has to go through the same point, and not only that, at that specific point, it has to have the same slope. So it needs to share a point and share the slope at that point. So in order to figure out the equation of the tangent line, so we need to come up with an equation for a line that has those two things in common. Shares the point, shares the slope at that point. The reason that we had to find dy dx is because what dy dx represents is the slope. We don't know what this function is in terms of, having y equals some function of x, but we do know that it's given by this curve here, this relationship between x and y. Well, we also know, based on the fact that we just found this dy dx, that this equation right here will tell us the slope of our function at any given xy pair that we plug in. So basically, if we plug in pi over 2 for x and pi over 4 for y into this equation here, that'll tell us the slope of our function at any given point, or in this specific case, at the point that we care about, pi over 2, pi over 4. So if we plug in the point pi over 2, pi over 4, which means wherever we see a y in this equation, we replace it with pi over 4. Wherever we see an x in this equation, we replace it with pi over 2. That'll give us the slope of this curve at this point. Well, if we do that, I'm not going to go through all of that. I mean, you can kind of see some of these terms are going to cancel out. It's not going to be terribly difficult to do that because, like for example, right here, cosine of 2y. Well, cosine of 2y is just going to become cosine of pi over 4 times 2, which is cosine of pi over 2. Cosine of pi over 2 is 0. Same thing is going to happen here with sine of 2x, which means if we do go through all of this and plug in this for x and this for y throughout this whole thing, what that is going to simplify down to is we are going to get, in the end, pi over 2 on the numerator. So this whole thing on the top here is going to give us pi over 2. And then our denominator is going to simplify down to pi. So when we plug in these on the bottom here, it's going to simplify down to pi. Well, this is the same as pi over 2 times 1 over pi. Because remember, dividing by something is the same as multiplying by its reciprocal, or 1 over that thing. So pi over 2 times 1 over pi is the same as pi over 2 divided by pi. Then these pi's cancel and we just get 1/2. So basically we know the slope of our tangent line needs to be 1/2. We also know that it needs to go through the point pi over 2, pi over 4. So if you know the slope of your tangent line and you know the point that that tangent line has to go through, well, you can just use the equation of a line, the point slope form, which is y minus y0, which is just some y coordinate that your line lies on, equals the slope times x minus x0, which is the x coordinate of some point that this line lies on. So we can replace y0 with pi over 4. We can replace m with the slope that we just found here, 1/2. X is just going to stay as x, and then we can replace x0 with the x coordinate we know that this needs to go through, which is pi over 2. Then we can simplify that, and doing that, if we simplify it and get the y all by itself by adding the pi over 4 over, we're just going to get y equals 1/2 x. So this is going to be the equation of our tangent line, which goes through this point. We know that it shares the point. We know that it's going to have the same slope because we found the slope using this dy dx. Therefore, that's going to be the solution to this problem. Just going to be y equals 1/2 x is going to be the equation of the tangent line. Well, I hope you found that video helpful. If you did, be sure to hit that like button and subscribe to my channel down below. Make sure you hit that bell icon as well so you're notified of all my new videos, including when I go live on Monday night at 5 Pacific. If you want to keep learning about implicit differentiation, I have made a few other videos about that. Go ahead and click on one of those over there, and I'll see you on Monday night.